The Aldol reaction. This is on section 17.4 on page 827 on Ogilvy's mechanistic patterns. This is a reaction where an aldehyde can react with itself in the presence of an aqueous solution of a base, such as potassium hydroxide in water. This produces a beta-hydroxyaldehyde, an aldehyde alcohol that we call aldol. For the correct mechanism, it involves the more significant resonance structure of an enolate ion, and this is given on page 827. These resonance structures were previously described in an earlier video. To view this reaction in a more easier way, think of the carbanion as a nucleophile that is made from deprotonation of the alpha carbon by the base. The carbanion nucleophile with a blue dot attacks the electrophilic carbonyl carbon with a red dot to form an alpha to beta bond. Protonation of this aldol alkoxide by water gives the aldol product. Ketones can also self-react to make an aldol product. This is on page 828 of Ogilvy's mechanistic patterns. Let's look at the reaction of acetone that can self-react to produce the beta-hydroxy ketone. Note, the equilibrium heavily favors the ketone reactant due to steric strain. Again, deprotonation of the alpha carbon by hydroxide base favors the reactants as the pK of the ketone is higher than that of the more acidic water. The formation of some of the enolate ion will go on to react with a carbonyl compound. In this example, the ketone is acetone. Remember, instead of reaction with an enolate ion, use the carbanion for simplicity. The carbanion is a nucleophile, but the ketone has alkyl groups that sterically hinder the accessibility of the electrophilic carbon. This is why the equilibrium heavily favors the reactants. Some ketone alkoxide is made, however. Protonation of the ketone alkoxide gives the aldol product, the beta-hydroxy ketone. The aldol reaction can also be acid-catalyzed. This is on page 828 of Ogilvy's mechanistic patterns. This figure gives the reaction mechanism. It is heavily detailed. Let's look at it step by step. The first step is the acid-catalyzed enol formation previously described in an earlier video, but again presented here. Protonation of the oxygen of the carbonyl allows water to deprotonate the alpha carbon to make the enol. The enol serves as a nucleophile at the alpha carbon, and the pi bond of the enol attacks the electrophile of an acid-activated ketone protonated at the oxygen. This produces a protonated beta-hydroxy ketone. Deprotonation of hydrogen on the alpha carbon gives an enol alcohol. It is the alcohol and not the enol that is protonated by acid. This gives a molecule where water is a good leaving group, and electron rearrangement produces the protonated enone, which is deprotonated by water to give the alpha-beta unsaturated ketone, the enone. Acid-catalyzed aldol reactions are not common in this textbook. The formation of the enone, alpha-beta unsaturated ketone, or the aldehyde will be discussed in the base-catalyzed aldol reactions.